Log on, tune in, find out. Another good idea from Cambridge.
This afternoon as well is Anders Hansen from the neighbor, I guess.
Yes.
Cambridge. And he will talk about generalized sampling and infinite dimensional compressed sensing.
Well, thanks very much. Can you hear me? Thanks very much to the organizers. It's been a great conference so far. I've had a great time. I'm going to be talking about generalized sampling and infinite dimensional compressed sensing. That is a new way of looking at sampling, and it's also a new way of looking at compressed sensing. This is joint work with Ben Adcock. Ben was a student here with me, and he's now in Canada. I'm going to start by giving you a little bit of motivation, and I'm going to start by the MRI problem. Now, the MRI problem I present to you for two reasons. One is that this is a conference on medical imaging. And the second reason is that this is really a fully, what should I say, analog or continuous or infinite dimensional problem. Now, the way we model physics is we model it with differential operators and integral operators, and the world is really an infinite dimensional object in a way, and the world is analog, you may say, but computer science is discrete. So when we're actually going to solve this reconstruction problem, we see the Fourier transform of a function that we would like to see. It is really the full infinite dimensional problem. And to solve it, we have to go through some kind of discretization. Now, that is a delicate subject, and that is really the topic of this talk. Now, if you have never heard about compressed sensing before, I'm going to give you sort of a 101 introduction to compressed sensing in 5 minutes. If you know compressed sensing very well, you can have a nice little nap in 5 minutes, and I'll wake you up. Compressed sensing, the way we understand it today, is really a finite dimensional theory, and it's about solving an inverse problem. Y is the observations. X0 is a vector that you would like to know, but you don't see that, and in between is a matrix. Now, the thing is, if you know that U is invertible, this is really not rocket science, and that's not what compressed sensing is all about. Compressed sensing is really about what if you don't know the whole Y, but rather some parts of it. And the idea is that we're not going to say, well, we're just going to know, say, the first three components on the vector. No. Well, we're going to allow ourselves to choose that randomly. So we choose random observations here, and that means that we open up the possibility that we may not be able to construct X0, but we would like to reconstruct it, and hopefully that's going to be with a large probability. So essentially what we do is that we take a set omega from 1 to n, choose that uniformly at random, and then project. So if omega is, say, 1, 3, 5, 7, then you pick up the first, third, 7, and 9th component of Y. The question is, can you recover X0 from those observations? Where does this come from? Well, this actually came out from medical imaging, in particular magnetic resonance imaging. And typically, the observations would be Y, the unknown would be, say, the Logan-Sheff phantom, and U, the discrete Fourier transform. Now, that is a discretization. It is not the true model for MRI. That's very important. I'm going to discuss exactly where this approximate model, how it enters MRI, but this sort of toy model was essentially a lot of the motivation behind this. Now, it would be a little optimistic to say that you could reconstruct any vector just from partial measurements. So there must be some extra structure, and the extra structure you're looking for is essentially sparsity. So I'm going to define this for future notation as well. So delta here is what we call the support of the vector, simply just the integers corresponding to the non-zero elements of the vector. And the idea is that we would like to have some kind of algorithm and then some theory saying that if we just see parts of the observations, we would like to be able to recover X0 with some probability. And the question is, how large should it be, the set omega? And that should intuitively be a function of n and the size of the support, how many non-zero components you have. Initially, people started looking at the L0 problem, if you hit U here with a projection on the left, that means that you suddenly have something which is non-invertible, meaning that there's plenty of candidates here that satisfies this. So you can search for the one that has the fewest non-zeros, the sparsest solution, if you will. You can write theorems about that. The only problem is that people in optimization will tell you that this here is a combinatorial nightmare to solve, and complexity theorists will talk about NP hardness. And essentially what one does is one abandons that problem and say, let's go for a convex relaxation of this, namely an L1 norm instead, and then one searches for the element that has the smallest L1 norm and satisfy this equation here. And I'm just going to show you a little theorem, which is quite grand, actually. It has been very, very famous. So this was the first on this kind given by Candace, Romberg, and Tao. And it says that for the discrete Fourier transform, they only prove this for the discrete Fourier transform, that the amount of measurements needs to be proportional to some constant, and then times the size of the support, and then log n being the dimension. It was a technical and rather difficult paper, and they only did this for the discrete Fourier transform. And it had been conjectured that this would also be true for arbitrary isometries, but then there should be an incoherence parameter that I'm going to talk to you about later on, and then n in front of here as well. This is a special case. So that was 101 compressed sensing. Now let's go back to MRI. So the crucial problem is we see the Fourier transform, we would like to get G. So what do we do, and what is the connection to sampling theory? Well, the way we do this is essentially to go back to the Shannon sampling theorem. And you may say, oh, do we really have to go through the Shannon sampling theorem again? Yes, because essentially what I'm going to show you is a generalization of this, but we depart at a rather fundamental level. So the Shannon sampling theorem says that we can recover both f and g through point samples of f. We have to sample at Nyquist. You sum up the sinc functions or exponentials here, and then you can recover the functions. Now, it is quite important to look at this here. This is typically, we're interested in G, our MRI problem. This is the crucial part, and up to a little epsilon here, this is essentially the Fourier series. So you can think about you're getting the Fourier coefficients of the function, and you would like to reconstruct it from there. We cannot take an infinite amount of samples, so we simply take a truncated series here, and we have an Fn and Gn. And essentially what we're doing is that we're using the truncated Fourier series, and that is the approximation. So to give you a little bit of motivation, I'm going to show an example. I'm going to take the simplest example that I can think of. I don't claim that recovering the Haar wavelet is something that people do a lot in MRI. This is only a toy problem, but to visualize the point I would like to make. The reason why I've chosen the Haar wavelet is that this is obviously something which is very sparse. I can look at this function essentially as a vector with infinitely many entries, but only one non-zero component, right? This is extremely sparse, okay? The task now is to think of this here as our phantom, if you will. We're going to try to reconstruct our G, the Haar wavelet, from its Fourier transform. How do we do it? The classical way is to go via the Shannon sampling theorem. We form our Gn. N is in this case 128. That means that I've taken twice as many samples. And here is Gn. You see the good old Gibbs phenomenon here. And here you have visualized the pointwise error slightly enlarged. Here you can see this. Nothing dramatic here. That's what to expect it. We have something which is discontinuous. You see the Gibbs phenomenon. And in particular, this Gn guy here converges rather slowly. And that is really the problem. We don't have uniformly convergence here, and we have really slow convergence. And whenever you see an edge, and in particular, whenever you don't have periodicity, the Fourier series converges slowly, and that is a problem. I would like to show you exactly where the discrete Fourier transform enters the model. the reason why people have worked a lot on the discrete Fourier transform, and it comes from this. We can write this here essentially as a matrix equation. What we'll do is that we'll take all these observations here, the samples of f, put that in a vector, and the unknown is now a vector which corresponds to Gn. It's really a vector containing pointwise values, pointwise samples on a grid of the Gn function. And the amount of samples, the length of the vector x corresponds to how many samples you've taken. And this guy here, which you see clearly from these exponential, now becomes, up to that epsilon, the discrete Fourier transform. That is how the discrete Fourier transform enters the whole problem. When you use the discrete Fourier transform, what you're doing is you're truncating the Fourier series. That's how simple it is. So if we had the observations here, just applied the inverse Fourier transform on the other side, you will get here a sort of pixel version of the Gn. That's how it works. So the keynote here is really that it is the truncated Fourier series that you use as an approximation for the function. We're going to try a little experiment here with finite dimensional compressed sensing. And what we're going to do, because we know that G is sparse, right? We secretly know that it's the Haar wavelet. So, but suppose we have the information that it was sparse in the Haar expansion, which it obviously is. It's tempting to say, what if I hit that x now with the discrete wavelet transform corresponding to the Haar wavelet? It sounds reasonable that this guy here then should be rather sparse, okay? So if that's the case, it's very tempting to try compressed sensing. So what we're going to do is that we're going to solve this L1 problem here. We're going to take random measurements of the observations. But now it's not just the Fourier transform, it is the discrete wavelet transform here as well. And the idea is that if this guy here now is sparse, we don't need to take a lot of samples. That's the hope. Now what happens? Let's see what happens. This is what happens. I have taken 130 samples. That's a little more than 50% of the samples. And I have reconstructed this guy here. That's not terribly impressive, thinking that our original guy was extremely sparse. 130 samples, and this is what we get. The question is, what went wrong in this case? Let's go back. Was the problem that we didn't take enough samples? What would have happened if we took all the samples? What would have happened if P omega here was the identity? Well, then everything here is obviously invertible, meaning that what you recover is x0, and hence we get our x. But what is x? X is a vector of pointwise values of this guy here. X is really Gn. There's no way that this function here is sparse in the Haar wavelet. This is a C infinity function with a lot of wiggles. So what we've done by doing this kind of discretization, we have taken the originally extremely sparse problem and completely ruined the key feature of the problem, namely sparsity. And that is the key point. So this leads us to some questions. The first one is this. If we know that G is sparse, doesn't have to be sparse. Life is really not sparse. It is sparse plus something. Typically you have rapidly decaying coefficients in some bases. And having said that, we've spent almost 30 years of research on finding alternatives to Fourier expansion, say wavelets. And it is possible to think that there are other bases that may be good, not just the Fourier. So if that's the case, like in our example, the question is, why do we use that one then? And the other question is, why do we use this sparsifying transformation here when it really doesn't help us because, well, we actually ruin sparsity? And the third question is really the heart of this. why aren't we trying to get the coefficients, these beta k's here, if I have a different basis? Why don't we go for those instead? Why do we use the Fourier coefficients? And I would like to visualize this to try to show you what I mean. So I'm going to use my incredibly poor drawing skills. Okay, so let's try. So this here now is a terrible attempt to try to draw an MRI machine. So the idea is that this is where the patient comes in, and I'm just going to say MRI in case it's not clear. Now this machine comes with a button. It comes with a button here, and it says Fourier. When I press this here, I take Fourier samples. That is what the MRI machine gives me. It gives me Fourier coefficients of what I would like to see. What would be kind of handy was that if we had several buttons on this, that could give us, say, Haar coefficients. Or another one, maybe, say, Daubercy. Say, Daubercy 4. Or maybe, say, polynomial, say, Legendre polynomials or something like that. The problem is that we can't build such a machine physically. The reason why we get the Fourier coefficients, it's from the physics. You know, if an engineer tells you how does the MRI machine works, he will show you an integral. So getting the Haar coefficients is not something that the physicist can make. He can't build that for us. So what I would like to show you is that we're going to try to build that machine, but we're not going to try to build it physically. We're going to build it mathematically. That's the idea. We would like to have a mathematical tool that can still give us those coefficients. That's the idea. And that's the idea of generalized sampling. So the model is as follows. Let's take a step back and sort of enter the abstract world and model this in a Hilbert space and say that what we would like to get is simply a vector. And that vector we can express in some basis, and it has some coefficients. Somebody has told us that, you know, this basis is really good for our image, okay? And we would like to get these guys. The problem is that we don't see it. The machine does not spit that out. It spits out something completely different. But it spits out something we can model. We can say that, well, Fourier coefficients, if something spits out the Fourier coefficient, it's just a linear functional, right? A linear functional acting on a function. So we say, okay, we have some measuring functionals, and that's what we see. And from those measurements, we're going to try to cook up a recipe for getting the other coefficients. That's the idea. So what happens? Well, this gives us essentially an infinite system of equations. You can think about these here as the Fourier coefficients of your function. These are the coefficients we want. We do have maybe some theorem saying that if we had, say, Haar, Daubercy, whatever basis you would like to have, these guys drop dramatically. So what do we do? Well, what we have is what we've got here. What we want is here, and between is this monster, this infinite matrix. So you can think about essentially as this as a change of basis matrix. In finite dimensions, very easy. In infinite dimensions, a little more subtle. How do we solve this? There are a lot of bad ways to solve this. I'm just going to mention one, which is the finite section method. It is very tempting to think that we can take n samples here, truncate this, say, take an n by n matrix, and then try to get n coefficients. Now, what would happen in that case? Well, there are a lot of things that can happen. The first thing is that if I take an n by n section of this, it may not even be invertible. The other thing that could happen is that it may be invertible, but as I let that section grow, the condition number blows up, typically exponentially. And thirdly, what happens is that you may be able to have an inverse here, but if you actually try to compute, you know, approximations to these coefficients, they don't converge. So you have an unstable, non-convergent method, and that's not going to give anybody tenure anytime soon, so we have to abandon that. So what to do? The reason why I came into this was I worked on a completely different problem. I worked on a problem in computational spectral theory. It had been an open problem from several decades, how to compute the spectrum of an arbitrary infinite matrix. You run into exactly the same problem. If you take an n by n section of an infinite matrix, it gives you garbage. What one has to do is to look at different techniques, and what I started studying was essentially how to use uneven sections and essentially rewrite the problem completely. This technique you can also work on when you want to solve linear systems. And I'm going to show you the idea. The idea is that if you try to take n measurements and try to compute n coefficients and you want a linear method, that becomes the finite section method. We need a little bit of wiggle room, and the wiggle room is as follows. I'm not going to take the same amount of measurements as the number of coefficients I would like to compute. They're going to be different, and that is the key. That gives us the wiggle room so that we can actually get something which is 1, stable, and more importantly, 2, convergent. The idea is as follows. Pn is the projection that simply takes the first n component, same thing with k, but they are different. I'm going to see n coefficients, and I'm going to try to reconstruct k. I'm going to see n observations, and I'm going to try to reconstruct k coefficients. Here you see the uneven sections. This is the infinite matrix, but what I have here is essentially a composition of different sections of it. It's a k guy here, and n here, and then the adjoint, but when I multiply these together, it's simply just one matrix. I can solve this, and now what happens, and this is the key, the difference between the guy that I want and the guy that we have here, which essentially now is created by summing up these guys that you have from here, is controlled by 1 plus some constant times the tail. So up to a constant here, which I'm going to comment on in a second, this would be as good as if I knew the k first coefficients of the betas. So if you have an estimate saying that you have rapid decay of the betas, this is where the reward is. That tail bound is exactly what we need. That's what we're looking for. If we had something that was completely sparse, now think about the previous problem we had with the Haar. If we took the Fourier coefficients, well, this guy here would be 0. It would actually be 0 for k equals to 2. And then we can actually tell you exactly how many samples you need. And this is based on the following. This ckn guy, the constant, actually tends to 0 as n grows for a fixed k. It's given by this, well, rather horrendous expression. You can actually compute it. This expression here is based on the first paper we wrote. Now we have a complete geometric interpretation, and we show that it's sharp and all that, but that's, I want to start with the beginning. You can mathematically prove things about this, but even without the proofs, you can actually do computations because you can actually compute it. And that gives us a theory which says exactly how many samples you need in terms of how many coefficients you would like to reconstruct. This leads to what we call the generalized sampling theorem. This theorem is an extension of the Shannon sampling theorem. In the Shannon sampling theorem, this matrix here, I'm going to show you, is going to be the identity. It says that you can take exactly the same samples as you would do in the classical Shannon, but you can reconstruct in whatever basis you want. That is the difference. And the way you do it is as follows. You create this infinite matrix, and now I don't do it on the line anymore. I do it in L to RD, important. So what we do is we create this guy here by taking the Fourier transform of these basis elements and evaluate them at some grid. We take some bijection from the natural numbers into this grid, and this grid is controlled by the epsilon, and epsilon Nyquist has to come in somewhere. It comes in here, and when that satisfies Nyquist, this guy here is an isometry. We do exactly as I suggested before. We're interested in getting the coefficients in our function g. We form this system of equations. And the bounds are given here. We can reconstruct approximations to both a g and f. This would be directly with these beta tilde coefficients. Here we take the Fourier transform using the same coefficients, and the bound in L2 is given by this. When you do L infinity on the F, there's a little extra term here that comes from the support of G. And this is the generalized sampling theorem. I just want to say that it is very nice to have a mathematical theorem telling you exactly about the relationship between the number of samples and the number of coefficients. That is quite interesting exercise in harmonic analysis to determine this. However, engineers can start doing this without the theorems, because you can actually do computations, and I just want to show you that. This is an experiment with a Haar wavelet. I have not proven anything. This is brute force computations. It shows here this here now is the number of samples. It's a number n as a function of k for the ckn to be less than or equal to 1. And what is fantastic is that is linear. It's actually better than linear. You see this sort of staircase growth, which is natural because it's a wavelet. That's what happens. We can't prove this yet. We do think we'll be able to do it, but it's quite tricky actually. But it doesn't matter. I can read, if I need 250 coefficients, I can read from this table exactly how many samples I need. And this is done numerically. We want to have theorems as well, but it's not like engineers have to wait for the theorems. They can start cracking numbers. You'll see that the growth is different. If you require that ckn is less than or equal to 2, then you have a sort of less steep slope, which is expected. Now I would like to show you a little example. Let's try it. So what I suggested earlier was that we wanted to build that machine, right? We want to build a machine that allows us to give us different coefficients. So let's try the experiment. This is now a G function. We would like to reconstruct it. The question is how and with what basis? So it is very smooth, it's even analytical, but it's not periodic. So Fourier may not be so good. Let's see how Fourier does. I've taken n equals 25. Well, this is what you get. This is the error. Not terribly impressive. And then you say, well, did you expect any better? It's a non-periodic function. But we have a new tool, right? We can reconstruct this in a different basis, based on exactly the same samples. That's the point. Which basis should we choose? Any suggestions? So it's analytic. So I would suggest something polynomial. Let's press the button Legendre and see what happens. This is the reconstruction. Looks pretty nice. I've taken exactly the same amount of samples. That's important. I haven't cheated. It's exactly the same amount of samples, but I've changed the basis. So the rather discouraging error from the Fourier series has now been turned into a rather nice. I mean, the error on the previous page was this, order 1. Here it's 10 to the minus 14. It's not like we have improved it by 14 times. We have improved it by 14 digits by changing the basis. And that's really the heart of generalized sampling. You take exactly the same amount of samples. We're not cheating, but we're changing the basis. If you have something that converges rapidly in a different basis, use that one. If your signal is a finite sum of exponentials, use Fourier. I don't have anything against Fourier. I love Fourier. But if it doesn't work, use something else. And you can do it. It's convergent and it's stable. When one talks about sampling theory in these days, in the age of sparsity, you cannot come with a new theory unless people ask you, can you subsample? And what we would like to do is we would like to subsample. The problem is that we can't just use the current theory nor the current method in compressed sensing for this, because it's just not a matrix. We have a different method, and that is the topic of the next part of the talk. What we want to do now is that we would like to do exactly as we did in generalized sampling. We would like to reconstruct in a different basis. We have the original infinite matrix. And we're going to try to attack that problem directly. So let's try to be maybe a little naive and say, what would we have done if we could actually use an infinite computer? Suppose now that we can do as follows. We can randomly sample some subset of integers. Those are going to be the observations. And we think now, just for the thought experiment, that we could actually solve an infinite dimensional optimization problem. What would happen if we did this? Well, first of all, I have to tell you how on earth do I sample. I'm going to sample a finite number from infinity. No, what we're going to do is that we're going to sample from finite, from some number. We're going to choose some n, and we're going to randomly sample from there. And then the question is, if I do that, how large should that n be, and how large should that m be? And the question is also, what if we do have a solution to the previous equation? If we could solve this here, what would be the error? What would be the error between what we want and what we would get? That is the crucial thing. So, obviously we can't, we can prove theorems about that. We can't compute with that infinite guy, but we can do as follows. We can say, okay, well, why don't I truncate that on the right side here? If I do that, then I end up with a finite dimensional thing that Jerome can solve for me. And the question is then, what would happen if we solve this problem here? What would happen to the error? What would happen as m grows? Note that, however, that has nothing to do with the sampling. The sampling happens here. This is a computational thing. So what would happen as m grows? And what would happen to the error? There's two models I would like to show you, and a couple of examples. The first one is what I call the semi-infinite dimensional model. This is as follows. We have a signal, x0, it's a vector, with a bunch of coefficients, but it is sparse. It is truly sparse. It has finitely many non-zeros. We have a delta here, and we do have an estimate of where they live. That is important. We don't know where it is, but we have some estimate on where they live. And the question is, okay, now I'm going to randomly sample, and I'm going to randomly sample from a set 1 to n. The question is, how on earth do I choose that? Suppose m is 59. How large should n be? 59? That is not a very good choice. That gives us a finite section method. That gives us rubbish. 50, well, 60, 61. What should it be? And then the question is, how large should m be? And we should also make sure that if m is equal to n, we should also be able to recover everything with probability 1. Now, this is really a toy model because the world is not sparse. It is sparse plus something. So this is the true model. This is a model where you have a signal y. It is something that's sparse plus something which is not sparse. But the point is that that h here should be controllable, that we have some control about the coefficients. That is a reasonable assumption of how the world actually looks. And if you think about a wavelet expansion and you look at the coefficients, that's exactly what you have. You have some spikes and then a little bit of small, then some spikes again, blah, 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 and things decay. So this is exactly what you have in those types of expansions. So this is really the interesting model. The other one is more of a toy model. I'm going to show you some examples before I show you the theorems. Let's just recall this because I'm going to use this here when I refer to equation 11. So we're going to randomly sample here. And so this here is omega, and here is m. This is the number of coefficients that we're going to compute when we do this L1 optimization problem. So we're going to do this as follows. The example I'm going to show you is this. I have a function g, and the function is a superposition of some Haar wavelets. And there's only 25 of them, and L in this here is 200. So there's only 25 non-zeros, and they're somewhere between 1 and 200. I don't know where, but somewhere there. And that's not a very interesting problem. I have added a little thing here, a cosine function, but to make it slightly more interesting, I've added a little discontinuity, just for fun. And the task now is to reconstruct my f. I could have reconstructed g, it's the same thing, but I want to show you an example with sinc functions as well. So we're going to form the Fn, which will be the classical Shannon sampling theorem. I'm going to sum up this with sinc functions. We sample at Nyquist. And then I'm going to give it two other functions. F tilde nk here is based on generalized sampling that I just showed you. That means that we take exactly the same amount of samples, but we reconstruct in a different basis, not sincs. I have a feeling that if we take the Fourier transform of the Haar wavelet, that's going to be good because we have the Haar wavelets in the G. That's the idea. And then I have my gamma n, and then capital M, which is a different function. That is taking exactly the same amount of samples, but we subsample. We take m of those randomly. And then we compute capital M coefficients different than that. These are very different functions. This here comes from a linear reconstruction. This comes from a nonlinear reconstruction. And here are the errors. N is equal to 601, equal in all of them. This is what happens with the sinc functions. And this is a problem which is very, very well known. Sinc functions do have terrible conversions, and this is the error. With generalized sampling, we have changed the basis. Now suddenly, it's a much more pleasant, can you see it? 10 to the minus 5, we gain roughly 5 digits. It's exactly the same amount of information. With compressed sensing, we subsample. So here we have computed 200 coefficients from 601 samples. In this case here, we take 230 subsamples from that and compute a higher number, 650 coefficients, but it's based on exactly the same amount of sampling. These are very different functions, but the error is roughly the same, and this guy here requires only 38% of the information that and that guy needed. So this is sort of the overall message. I just wanted, before I show you the theory, this developments did not happen in a vacuum. If you have read papers by, say, Aldrobi, Unser, Eldar, Grukenik, these things generalize a lot of that very, very nice theory that they have had. You may have heard about invariant subspaces. In invariant subspaces, that infinite matrix becomes a Toeplitz matrix. So this is just a special case of what you have here. Then the finite section method actually works. I want to show you something about the theorems. The important thing, this is the first one, is for the semi-infinite dimensional. The question is, how large do you take your n? That comes from these conditions. And then you will have, as you would suspect, this is the incoherence parameter. You're going to have the size of the support, and then there's a log thing, and that log thing is not n anymore. It's m times n, and this term here as well. But there's an m here in the denominator. But the important thing here is really understanding how you take your n. This has a corollary, which, if you don't care about infinite dimensional problem, but you only care about the finite dimensional problem, you may take comfort in that the conjecture results are actually true. This follows directly from the previous theorem, and then you'll see this is exactly what you will expect in finite dimensions. For the case of the discrete Fourier transform, this guy here is 1. So you recover what you had from before. So as I said, these things did not happen in a vacuum. These are just generalizations of the theory that was before. I want to show you one extra example before we quit. So whoops. This is the theorem for the full infinite dimensional problem. Conditions on how to choose your n comes from here. Then your m is replaced with this nasty looking thing here, which can be simplified if you actually want to do computations with it, but this is really what you need for the full infinite dimensional problem. And finally, I would like to show you a little MRI reconstruction problem. So here is my phantom. And you may object and think that that does not look very much like a brain image. And if this really is a brain image, then one should probably seek a doctor. So I would just want to point out that there's more to MRI than just medical imaging. In Cambridge here, we have a big magnetic resonance research center filled with engineers, and they don't care about brains at all. They care about chemical reactions. So this is exactly a type of thing that they will look at. They simply have a function. It could be something that is temperature, for example. and the chemical experiment is happening in some box. They don't see it, they see the Fourier transform. They use an MRI machine to monitor what's happening. So this is a toy problem for this. What we've taken is, I call it an infinite resolution image because it's simply a function. At every little point here, there's a function value. Simply taken some tensors of sine functions. This is how it looks. But I've made it sparse just for fun. There's only 70 of these guys that are non-zero, and everything above 700 is 0. So this is truly a toy problem. I want to show you how the classical MRI would work on this. This is the original guy. This is the G. This is how it looks. This is the truncated. I have taken 501 by 501. That's roughly 250,000 samples. And this is the reconstruction. Can you see any difference? Very hard to see because MRI works very well, but I had to take 250,000 samples. If you enlarge it, you see the difference. You see both from the pixels and that we haven't taken enough samples, so you don't get the right color. That's the problem. You know, N should have been much larger. But 250,000 samples are quite a lot. It is tempting to use the standard finite dimensional compressed sensing of this. If you use L1, you get complete rubbish because it's not sparse in that at all. Just want to show you what happens with TV. I have sampled 50%. This is TV. This is the original. And the reconstruction is sort of in the ballpark, but still quite far away from the true solution, even with just 50% of the samples. So what one can do is as follows. Well, we do the trick. We form this infinite matrix that we had of ours. We choose an N. We have a theorem to guide us how to choose that. This is 15,000, which is much less. We're actually taking much less information, but we're even going to subsample from that information. We're going to subsample 500 coefficients of that. And when you do the reconstruction, I plug this in, and this is what I get. And then you see, that's not perfect, is it? Now that's true. That's the best I could squeeze out of the software I had. This was done, I think, by CVX, which is a fantastic thing, but you can't get more than 8 digits on it. So what I'm going to show you now is the original. This is the reconstruction. Hard to see any difference. But you really have to enlarge it to see any difference. This is the original. This is the classical with Fourier, 250,000 samples. This is the reconstruction that we computed with infinite dimensional compressed sensing. This takes 500 samples. And it's now, well, I did actually give, this picture here is what I computed, so it's 8 digits away from that, but that's very hard to see. So that's sort of the whole point. To sum up, the take-home message is, yes, you can reconstruct in arbitrary basis. Yes, you can subsample. And with that, I thank you so much for your attention. Thank you.
It's just a small point. I didn't quite understand when you had the analytic example.
Yes.
That you computed the Fourier series, and you said we don't expect it to work very well because it's not periodic.
Indeed.
I don't understand why you said periodic. It has a periodic extension. Surely the point is it's not close to a trigonometric polynomial.
No. Maybe I wasn't clear. If you want to analyze the speed of convergence of the Fourier series, this, right? You'll normally do it on the circle. That means that if you should do it on a circle, that point should be the same as that.
Right, yeah.
So this guy here doesn't satisfy that.
Has a jump.
Exactly. So what this is really is thinking about that as discontinuity. And that is the whole.
It's not smooth as a period. Its periodic extension is not smooth.
Indeed. So that's the point. And the reason why I did this was to show that even with infinite smoothness, even with analyticity, a jump destroys the speed. That's the whole point. So in an image, could there be a jump? Quite likely. That means that the Fourier series will converge very slowly, and then change the basis. That's sort of the message. Yeah.
Any more questions? If not, then we thank the speaker. I personally would like to thank both speakers of this afternoon session because they kept their schedule very well. Both of them used 2 minutes less time that they would have. Very nice. And we need to thank all the speakers of this wonderful workshop that we have just been. So let's give a big hand to all the speakers.